Have you ever stopped to think about how you can watch a movie streaming from a server that's thousands of miles away and it just works flawlessly? Well, today we're pulling back the curtain on the invisible rulebook that makes our entire digital world possible. I mean, seriously, think about it. It's something we do 100 times a day. You click a link and a website from halfway around the globe just appears on your screen. But how? How does that data know how to get to you? What keeps it from just getting lost out there in the digital void?
Well, it's not magic, but it's pretty close. It's all thanks to a kind of universal language, a silent four-step agreement that every single computer, phone, and server on the internet follows so they can all understand each other. Let's get into what this digital rulebook is all about.
So, this foundational set of rules, the very bedrock of our digital lives, it has a name. It's called the TCP/IP model. TCP/IP is basically the master plan for how data gets from point A to point B online. You might also hear it called the DoD model, and that's because it was originally developed by the Department of Defense. It's the whole reason your Apple device can talk to a Windows machine or your Android can chat with an iPhone, no questions asked.
And the backstory here is actually pretty cool. It was born back in the 70s. The US military needed a totally bulletproof way for different computer networks to communicate, even if parts of the network were damaged. That built-in focus on reliability is a huge reason why it's still the engine of the internet today.
Okay, so what does this rulebook actually do? The best way to understand it is to follow a single piece of your data on its incredible journey. You see, the TCP/IP model breaks this whole trip down into 4 distinct layers, and each one has a super important job.
So, our journey starts right here, at layer 4, the application layer. This is the part you actually see and interact with. Your web browser, your email client, your file sharing app, that's all happening at the application layer. This is where your request is born.
And you've definitely seen the languages or protocols of this layer before. Things like HTTP for websites, SMTP for sending an email, or DNS, which is basically the internet's address book, turning a name you can read into a number the network can understand. Now, once your data is created, it gets passed down to layer 3, the transport layer. I want you to think of this layer as a super efficient shipping manager. Its job is to take the data, chop it up into smaller, manageable chunks called packets, and get them all ready for their big trip. Now, our shipping manager has 2 main options. For something really important, like an email, it uses TCP. That's like sending registered mail. It checks to make sure every single packet arrives safely. But for things like video streaming, where speed is everything, it uses UDP. That's more like sending a postcard. It just sends the data as fast as possible and doesn't wait for a confirmation.
All right, next up, our packets arrive at layer 2, the internet layer. You can think of this as the global navigator. Its one and only job is to be a GPS for your data, figuring out the absolute best path for each packet to take across the vast, complex web of the internet.
And this is where the famous IP address comes into play. Every single packet gets stamped with the source and destination IP address. These are like unique street addresses that routers all over the world use to pass your packet along, getting it closer and closer to its final destination.
We're at the final stop of the journey, layer 1, the network access layer. If the internet layer was the global GPS, think of this as the local delivery truck. It handles the last mile, the physical part of the trip, turning all that digital data into actual electrical signals, radio waves, or pulses of light. Yeah, this layer is all about the physical hardware. We're talking about the Ethernet cables plugged into your computer, the Wi-Fi signals in the air, the fiber optic cables running under the street. This is where the ones and zeros actually get sent out into the world.
So, now that we've met the whole team, let's see how they all work together in a beautiful, coordinated dance. This process of each layer adding its own bit of info to the data is called encapsulation.
So picture this. You type a web address into your browser. The application layer creates an HTTP request. The transport layer chops it into TCP packets, adding port numbers. Then the internet layer slaps on the IP addresses. And finally, the network access layer sends it all out as electrical bits over your Wi-Fi. It's an unbelievably elegant process, and it all happens in the blink of an eye.
So that's the how. But why? Why did this particular model become the gold standard for the entire internet? Believe me, it wasn't the only option out there, but it's the one that won. Let's figure out why. You see, before TCP/IP really took over, there was another big contender called the OSI model. It was a lot more theoretical, more academic, and it broke everything down into 7 different layers.
But as we've learned, TCP/IP streamlined everything down to just 4 practical layers. And you know what? That focus on practicality turned out to be its secret weapon.
And this really gets to the heart of it. The 7-layer OSI model is a fantastic reference, a great way to think about networking. But TCP/IP, the one born from the Department of Defense, was designed for the real world. It was meant to be implemented, to get its hands dirty, and that's exactly why it took over.
And this is why it's at the heart of everything we do online. It's incredibly reliable, it can scale from your tiny home network to a global one, and it just plays nicely with pretty much any device or operating system you throw at it. It's flexible enough to adapt to new technologies, which is a testament to just how brilliant its original design was.
At the end of the day, it really all boils down to this simple idea. TCP/IP is more than just a technical model. It is, quite literally, the language of the internet. It's the reason we can have this amazing global network where anyone can talk to anyone else.
And that leaves us with a pretty fascinating question, doesn't it? This digital language was created over 50 years ago, yet it's more powerful and more relevant today than ever. So as our world gets more and more connected, what's the next thing we're going to teach this language to say? What's the next chapter in the story of the internet?